All right, here we have the notes for section 1.2, functions and their properties. So first we got the definition of a function. So a function from a set D to a set R is a rule that assigns every element in D to a unique element in R. The set D of all input values is called the domain, typically your x's of the function, and the set R of all output values is the range or the y values of the function. So if you look at these two images, this one describes a function. Each x value is mapped to one y value. Over here, this one's not a function because x1 here is mapped to more than one y value. So every element to a unique element in R, meaning each x value can only be paired with one y value, or one y value. This is function notation. Y is a function of x. X is the independent and y is the dependent. So example 1 here, does the formula y equals x squared define y as a function of x? So is every x value assigned one individual y value? So if I plug, say I plug 2 in for x, is it possible to get two different numbers for y? It's not, because if I plug 2 in, I only ever get 4. So this one would be yes. If we do a t-table, no x value gives you more than one y value. All right, so example 2, that should be of the 3 graphs shown below, which is not the graph of y as a function of x. How can you tell? It's this one. This one is not a function because, for example, here at x equals 0, there are 3 different y values. It's up here, it's slightly more than 2, it's equal to 0, and slightly less than negative 2. So one x value, 0, has multiple y values assigned to it. So this one is not the function. That's what's referred to as a vertical line test. So this is a graph, which is the set of the points xy, and the plane xy defines y as a function of x if and only if no vertical lines intersect the graph at more than one point. So here, I can draw many vertical lines that cross the graph at more than one point. So it is not a function. So domain and range. So for domain and range, domain is the values that are allowed to be plugged in for x. So typically there are some things you need to be careful of. Those are square roots and fractions, because you cannot take the square root of a negative number and you cannot divide by 0. So those are going to put restrictions on your domain. So for example here, for f of x, the square root of x plus 3, you cannot take the square root of a negative number. So what you do is you take the inside of the root, whatever it is, and set it greater than or equal to 0. And then you solve that expression. So for this, x must be greater than or equal to negative 3. That's the domain. For g, I actually have 2 things to check. I have the root, so pull its inside out, set it greater than or equal to 0. So that one's done. But I also have the fraction. The denominator of the fraction cannot equal 0, because then I would be dividing by 0. So x must be greater than or equal to 0, and x cannot equal 5. So you can use any number in that equation as long as it's greater than or equal to 0 and not 5. Now the last one here is actually this last part here, where you have 4 models. We use a domain that fits the situation, which is the relevant domain. So this a of s is the square root of 3 divided by 4 times s squared, where a of s is the area of an equilateral triangle with side lengths of s. So the domain for this problem is s is greater than 0. It's that because if you're talking about if s is the length of a side of a triangle, s isn't going to be a negative number, and you can't measure, triangles won't have 0 side length. So s has to be some positive number more than 0. So that's why, even without having to do any math, that still has to be true. Lengths aren't negative, and they have to be more than 0. Oops. All right. So example 4 says find the range of the function 2 over x. So the easiest way to find range is actually to look at a graph. So let's see if I can get, there it goes. Okay. So we'll graph 2 over x, and look at the draw. So if you get that graph, so range is the y values. So if you look at my graph, it flattens, starts real low here, then drops off the bottom, and then starts back up here, and goes that. So there's actually one y value that never gets used in this equation, and that is 0. Because the graph has that break, there's a horizontal break on the graph at y equals 0. So for this, the range is y not equal 0. All other values will work. Okay, the next part here deals with continuity. So functions that are graphs that are continuous is a graph in which you do not have to lift your pen or pencil at any point in time to draw it. So this one is continuous because I can trace along the curve without having to lift my writing utensil. These two are examples of removables. So here I have to lift my pencil up to take care of that open circle, and then I can keep going. Same thing happens here. These are both removable because I can get rid of that hole. In this case, I can just move this closed circle down to fill it in, and this one I can just essentially write an extra addition to the equation to fill the value in. Like I say, at x equals a, f of x has to equal whatever that number is. I can change the value. The next ones are actually ones that are not removable. So you have the jump discontinuity, where the graph jumps in value, jumps up here. You can't move an entire equation. You can move a single point, but you can't slide this entire piece down. This one is an infinite discontinuity, which is actually what we saw on the 2 over x equation, where the graph goes to infinity or negative infinity at some value. All right, so example 5 here, which of the graphs below show functions that are discontinuous at x equals 2? Are any discontinuous removable? So this one is, because it has an infinite discontinuity, which is not removable. These other ones are, so this one is continuous everywhere, so that's the problem. This one is also discontinuous, but this one is removable. Because I would just have to fill in that little hole, and my value would be taken care of. Okay, increasing, decreasing literally means what you're talking about. Increasing means the graph is getting larger as you read from left to right, it's climbing. Decreasing means the value of the graph is falling as you read left to right. The other option is constant, which the graph is flat as you read to left to right. So you can put them all together and get a combination. So this graph is decreasing until you reach -2, then it's constant, and then it is increasing. Okay, so example 6, for each function, tell the intervals on which it is increasing and is decreasing. So I need to draw graphs for this. So quantity x plus 2 closed quantity squared. So it's going to look like that. So it hits the value there, so that's -2 right down there. So this graph is decreasing when x is less than -2, to the left of -2. It is increasing when x is greater than -2, to the right of -2. All right, so the second one here, we've got, let's see here, x squared over x squared minus 1. So, looks like that. Okay, so I'm going to zoom in a little bit. There it goes. That's a better picture. So this graph, as I read from left to right, so I have one section here. So that is increasing when x is less than -1. And then I have this piece here, which is also increasing. But that's between -1 and 0. If you notice, I can't combine them because the graph breaks, so that's why I can't just hook these two things together and call it just x is less than 0. And then I've got, this piece over here, so that is decreasing, 0 less than x less than 1, and then the second piece also x greater than 1. That's this piece right here. It is decreasing as I read from left to right. All right, so now we have boundedness. So bounded refers to if there is a boundary the graph does not cross. So this graph is similar to the one we just had. That one is not bounded above or below because the graph rises forever or falls forever. This graph is bounded above. It never goes over whatever this value is. This one's bounded below because it does not ever go below that value. And this function is just referred to as bounded because it is bounded both above and below. It does not spike in either direction. All right, so 7, identify each of these functions as above, below, or just bounded in general. So we're going to need some graphs. So 3x squared minus 4, draw. So that graph gives you a level parabola, so this one is bounded below. There is a lower limit to the function. And then we'll do this one, get to focus hopefully. That's x, well, x over 1 plus x squared. So that is bounded in general. It never goes above or below a given value. All right, so local and absolute extremas. So these refer to the maximum and minimum values of a function. So local maximum is the largest value in the area. The local minima is the smallest value in the area. Now, if they are absolute, that means they are overall the largest and smallest. So you can have multiple local maximums, but only one absolute maximum. You could have multiple local minimum, but only one absolute minimum. One of them is going to be the smallest minimum. One of them is going to be the largest maximum. All right, so example 8, I decide whether that function has any local maximum or minimum. If it's so, find the local maximum value or minimum value and the value at x at which each occurs. So you're looking for the points at which it happens. So let's see here. Type my equation in. X to the, to the fourth minus 7x squared plus 6x. Draw. So it looks like that. Zoom out just a little bit. One more time. Ooh, one more time. There it is. Okay. So this has two local minimums. There's one here and one there, and one local maximum there in the center. So I'll let my calculator find it. The maximum occurs there. So there is a maximum at 0.46, comma 1.3. There are two minimums. There's one at negative 2.06, comma negative 24.1, and there's another one at 1.6, comma negative 1.77. So I just use my calculator. All calculators have a maximum minimum value. Either that or you'd have to just essentially estimate the graph. All right, so we've got symmetry here. So this first one is y-axis symmetry, so it's mirrored across the y. The second one is x-axis symmetry, mirrored top to bottom. And then the third one is origin symmetry, mirrored across the origin, upper right to lower left. Now, the math behind this is actually relatively straightforward. Origin is referred to as odd, and y-axis is referred to as even. So it says, tell whether each function is odd, even, or neither. So to check this, what you do is you pick some value for x, and you check these three things. You check f of x, check, f of negative x, and then negative f of x. So if I do 1, if I plug 1 in, 1 squared minus 3 is negative 2. If I plug negative 1 in, negative 1 squared is 1, minus 3 is negative 2. If these two match, your function is even. So down here, we'll do f of 1, f of negative 1, negative f of 1. So you notice I didn't do the last one because I don't need it. But if you need to do it, the last one's always the opposite of the first one. So that one would have been positive 2. So if I do f as 1, that's going to be 1 minus 2 minus 2. So that's 1 minus 4 is negative 3. If I do negative 1, that's 1 plus 2 minus 2, or just 1. And this one is the opposite, so that's 3. So this one is neither. Odd will happen if the bottom two match. So for this, f of 1 is going to be 1/3. F of negative 1 is going to be negative 1/3. And negative f of 1 is the opposite of this, which is also negative 1/3. So these two are equal, so my function is odd. Okay, asymptotes. An asymptote is a line that the graph approaches but does not cross. So if we look at our equation here for this one, you have x over x squared minus x minus 2. I'll zoom in. Okay, so it looks like that. Okay, so there's my graph. So this has a horizontal asymptote. As you read off the left to the right, this graph flattens out at y equals 0. The vertical asymptotes occur where the graph spikes, like what vertical lines doesn't the graph cross. There's actually two of them. There's one here at negative 1. The graph will approach negative 1, but not cross negative 1. And there's another one over here at positive 2. The graph will approach positive 2, but not cross positive 2. Okay, and the last thing I believe, end behavior. Yes, last thing. So determine end behavior. So what end behavior means is as the x value gets very, very large. Now when that happens, all that matters are the lead terms in the numerator denominator. So this becomes 3x over x squared, which is 3 over x. You can reduce. Going over here, this would become 3x cubed over x squared, which is 3 over x. Down here, this would be 3x squared over x squared, which is just 3. And this one is 3x to the fourth over x squared, which is 3 over x squared. Now, the reason that happens is that if x gets really, really big, say x is 1,000,000, squaring 1,000,000 and then adding 1 is essentially the same number as 1,000,000. So you can ignore the plus 1. And that's actually true for anything that's not the lead term. Like, it doesn't matter if that have an x in it either. X squared is always going to be way more than x, so you can ignore the value that x contributes when the value for x gets very, very large. When x is small, like 1 or 2, that plus 1 matters. But when x is 1,000 or 1,000,000 or 1,000,000,000 or infinity, these plus 1s don't matter anymore. So they can ignore them. Infinity squared plus 1 is the same thing as infinity. The plus 1 does not change the value. So that is the end of this section.